Okay, so we started on cartography last time. Ideas behind maps. Now we're going to go into different kinds of maps, map projections. And again, the huge problem in cartography, the universal age-old problem. How do you project a three-dimensional image on a two-dimensional piece of paper? How do you project it on a flat map? Now, when you're looking at a small area, that's somewhat easier because the say like a road map of Arkansas or a city like El Dorado or Little Rock, it's easier to project three-dimensional world onto a two-dimensional surface because the curvature of the Earth is not so great that it becomes noticeable on a street map. So you can project that fairly easily. Everything on a fairly equal and representative scale. So because you're trying to project a three-dimensional image onto a two-dimensional surface, there are a lot of different ways to do that. But the problem is this: they're all distorted to some degree. So on something like a huge world map, like say like this one, how much distortion are you going to have? So it comes down to the question, what are you trying to show on your map? What are you trying to measure? What kind of scale is trying to show up here? And what kind of information is it you're looking at? So the question is, how much distortion you want to live with, and what's the point you're going to make? So flat maps cannot portray both exact shape and exact distance. Either one or the other will be distorted. I go here to Appendix 1 in the back of the book. It shows kind of several ways they make projections and so forth. But one form is the equal area or equivalent projection. Shows the correct area relationship but distorts shape. As an area may be square on a globe but rectangle on an equal area projection. Classic example of that here is the Mercator projection. It's the one here at the top. Zoom in on that. But basically, in terms of shape, that's what it would look like. But the distances are distorted. They're exaggerated at the extremes of north and south. So Greenland looks like it's the size of Africa, when of course it's very, very tiny. Greenland's fairly tiny compared to Africa. Continental United States is 1/5 the size of the continent of Africa. So you can't really measure distances very well. But you get the idea of the relative shape. And again, with maps, while finding distance is an important part of some kinds of maps, with other kinds of maps, the idea is showing relationships to each other. Like on the Mercator projection, it's showing where are these countries in relation to one another. Actually, another form of this is the Miller cylindrical projection. Here at the bottom here. It basically tries to correct the major problems of the classic Mercator projection by expanding the distance here at the middle. Try to for example, give Africa a more realistic size compared to the United States and other countries. But again, you still have that distortion of the poles. It makes it look like Antarctica takes as most of the land mass of the world, when actually it doesn't. Now, Mercator projection, it's often used for marine navigation because all the straight lines and maps are lines of constant azimuth. But Miller cylindrical projection, you have the meridians and the parallels, again, still are straight and all meeting right angles, but the straight lines aren't a constant azimuth. Shapes and areas are somewhat distorted. So the directions will only be true along the equator. And the Peters projection, again, just basically it's the opposite of the Mercator projection. Basically, here at the top, you see it's trying to show where the Earth is kind of curving away, and tries to show the size of Africa and South America, but does that by minimizing the size of North America and Europe and Asia. And the shapes, again, are fairly distorted. It emphasizes area exaggerations in high latitudes by shifting the standard parallels to 45 or 47 degrees. Again, that's the Peters projection. Here at the top. And you have the Eckert-4 equal area projection. This is used for world maps as a pseudo-cylindrical equal area map. The central meridian, this is the prime meridian, is straight. But the 180th meridians are semicircles, and other meridians are elliptical. The scale's relatively true along the parallel at 40 to 30 degrees north and south. Again, this one down here at the bottom. This map here would be a roughly an Eckert equal area projection type map. You can see the curved at the extremes of the 180th meridians, but straight along the prime meridian. Everything else curved. Next, then another one. Takeoff on this is the Berman cylindrical equal area map. And at the bottom, the classic Mollweed equal area projection. Again, instead of everything being straight like the Eckert equal area projection, its central meridian is straight. The 90th meridians are circular arcs, and the parallels are all straight, but unequally spaced. And it got the Robinson equal area projection, again kind of a takeoff on the Eckert equal area projection, so forth, like this. Top. It's based on tables of coordinates, not mathematical formulas. The projection distorts shape, area, scale, and distance in an attempt to balance the errors of projection properties. Basically, it just tries to split the difference between all these other projections. And then the sinusoidal equal area projection. Basically, projects the Earth as kind of a diamond shape. It has straight parallels at right angles to the central meridian. Other meridians are sinusoidal curves. The scale is only true at the central meridian and the parallels, and it's often used in countries with the larger north-south and east-west extent. Just here at the bottom. Next, you see what they're trying to do here is it's a geometric projection. And there are three types of geometric projections. That's what you can see here from Appendix 1. The cylinder, the cone, and the plane. Cylinder is basically as if you take the Earth and around Earth and basically turn it into a cylinder. Or the conic projection, just basically into a cone shape, like this, or just a flat plane. Now, one way of looking at this is thinking of a map projection by imagining a transparent globe with a light source inside it and a sheet of paper touching the globe. And one of the ways shown here is it's cylindrical, conical, or planar. Like I said, the globe grid and the outline of the continents be silhouetted in the paper on the map. Now, most of what we saw here, especially with the Mercator projection, that would be a cylindrical projection. Conic projection, again, it's like turning Earth into just a giant cone. Basically, it's the closest in form to one half of a globe. So they're all conic projections are often used to depict hemispheres or smaller parts of the Earth. Conic projections are widely used because they can be adjusted to minimize distortions. It can be either equal area or conformal. But by their nature, however, they can never show the whole globe. In fact, they're most useful for generally restricted maps of mid-latitude regions or greater east-west and north-south projections. So I'll go back to these here. Got the equal area projection. But you got the conformal projection as well. Again, what are you trying to show on your map? What's its purpose? Now, conformal projections preserve the angles between objects and shapes of small areas. Larger areas usually have some degree of distortion. The regions and the features generally look right and have a connection, correct directional relationship. And you have equidistant projections. Equidistant projections show the distance in all directions, but only from one or two central points. Now, two things about maps. One, maps can't both be equivalent and conformal. Maps can't be both of these. And maps can't both be equal distant and equal area. Give an example here from Canadian geography. Take the province of Saskatchewan. It is defined by very specific meridians and parallels. Basically, it's a rectangular shape. But the problem with Saskatchewan is because it's on a globe where the meridian, the parallels are shrinking as you get closer to the North Pole, it's not a rectangular shape. The northern border of Saskatchewan is shorter than the southern border because it's going up, getting closer to the poles. Even though, by definition, if you put it on a flat surface or on a Mercator projection, it'd appear like a rectangle. But in reality, it isn't. So to make this map, you have to give up one thing or the other. Especially in a huge area like Canada. And you also have what's called an azimuthal projection. An azimuthal projection, and remember what azimuth is, it's the angle formed at the beginning point of a straight line in relation to a meridian. It's based on that. Azimuth is used all the time in navigation. Ships and planes and everything else. Usually in relation to the meridian. In relation to a north-south line. Okay. So that's what we got here at page 6 here. This one we only see one hemisphere. That is an azimuthal projection. And it's very useful, particularly looking at a major geopolitical situation, like say the relationship between Russia and the United States. Not necessarily looking at each other across the Atlantic Ocean, you're looking at them from the other angle, from the Arctic Ocean. And this is why during the Cold War, so many nuclear missile silos are placed in places like Montana and North Dakota. Because, looking at this azimuthal equal area projection, the shortest distance between the Soviet Union and the United States would be, the mainland would be from the north, crossing the polar region, coming back down into the United States. Now, the Lambert azimuthal equal area projection is sometimes used to map large ocean areas. The central meridian, again, is a straight line. Um, Now there's a curve. A straight line is drawn through the center point is on a great circle. So it's showing the world as it would look like if you're out in space and looking straight down at one of the poles, North Pole or South Pole. Another example here would be here on this map here. These here at the bottom, these are azimuthal projections. Here you get to see Antarctica in its true shape and form, its relative size. You don't see it as taking up most of the land mass of the Earth as you would in this projection, but you see it as it would relatively be. Not too large, relative shape intact. Basically, if you're looking down at the Earth from the South Pole, map of space. Now, another form of azimuthal projection would be the orthographic projection. This here at the bottom. Now, they're used for perspectives of hemispheres. Area and shape are distorted somewhat. Distances are true along the equator, other parallels. Essentially, they're trying to give a more accurate view of what it would look like if you're approaching the Earth from orbit, approaching it from deep in space. That's basically what you would see. But again, the problem is you can only show one side of the Earth at a time in this kind of projection. And yeah, there is still some distortion. Again, the problem, 3 dimensions onto 2 dimensions. Now going back to the next one, conic projections. Again, the cone shape here. Example here would be the Lambert conformal conic projection. Here at the top. The thing about conic projections is you have to start from a particular spot. Basically, turn it into a cone and basically unwrap it. Now the thing about these is the area and shape are distorted away from the standard parallels. Directions are true only in limited areas. Usually often used for maps of North America. You can see still a lot of, because it's a curved map, it tries to preserve shape as much as possible, but you still have all the problems, the distortion. Now this is the polyconic projection using a central meridian at 100 degrees west. This one here at the bottom. The polyconic projection is used for most earlier U.S. Geographic Survey topographic quadrangles. The projection is based on an infinite number of cones tangent to an infinite number of parallels. Basically, instead of just putting one big cone on, it's basically, suppose the entire Earth are made of these cones at every conceivable spot. So the parallels are non-concentric circles. Scale is true along each parallel along the central meridian. As you get further out, it's more and more distorted. And here, last page, the space oblique Mercator map. It's a projection designed to show curved ground track of Landsat images. Essentially, they use these different images different ways, also to track satellites and so forth. There's a little distortion along the ground track, but only within the narrow band of the Landsat image. distorted there, but they use that for these different purposes. So yeah, a lot of different kinds of maps, because there's a lot of different ways to project this information, a lot of different needs for it. Now, every good map is going to have, among other things, a key, which is information presented on a map. The city size, different landforms if they're, sometimes changes in elevation. Sometimes noting that a star shape be used as a indicate a capital city. Just whatever else you're using, different landmarks of interest and so forth. That's a key. But also you have scale. It's used with all different maps. This is the ratio between reality and what is represented on the map. There's all sorts of different ways to do it. Say 1 inch could equal 1 mile, particularly on like a city street maps, or 10 centimeters equaling 1 kilometer. Often use a graphic scale. For example, this is the key here on this map here at the bottom. But here at this little corner here, that indicates the scale. Sometimes a numerical scale just kind of show you relative distances. It also shows you all this information. What is this in relation to reality? On this map, 1 inch equals 1,200 miles. Because obviously you can't have a one-to-one projection. We'd have the entire map would fill the entire room and the entire world. So just down this 1 inch to 1,200 mile square scale map. And you look at these keys here in these maps around the room, they generally have the scale as well as a key. The thing is though, with large scale map, it shows areas considerable detail, map of a city, so forth. But on a small scale, you can't have very much detail. Countries and continents, that's about it. Because this map is trying to portray the entire world on a relatively small piece of paper, there's a lot they have to leave out. But on a street map, they can include all these details, all these little towns, highways, byways, and everything else. Some maps, enough scale, yeah, they can show not only the streets, but relative shapes of buildings, names of all these different buildings and streets, addresses even. Something really popular at the beginning of the 20th century called the Sanborn Fire Maps. And that was a series of maps produced for each city in the United States by something called the Sanborn Fire Insurance Company. They produced these maps for cities and for insurance purposes to show where all these structures are located in relation to fire departments and what is in a city, so they can figure out what kind of insurance rates they can charge. But also for cities to know what structure is in a particular area. Especially if you're living in a large city, you have new structures coming up all the time, old ones coming down, and everything being changed and modernized and adapted. You may not necessarily know what building is at 232 North 63rd Street. You may not know that. Just don't get out in that neighborhood very often. Even in small towns, there are a lot of neighborhoods you don't go into because you just don't need to be there. You go home, you go to work, you go to school. Why would you need to go to the opposite end of town when you don't need to? So that's what that scale on the fire maps was about. Now, scale can be put in terms of call a representative fraction. So give them two numbers. First may be distance. First will be the map distance. Second will be the real distance. Example of our big map here. 1 inch equals 1,200 miles, just as an example. Or may see something like a 1 to 35 scale or 1 to 35 scale. If you've ever played with models or with Matchbox cars and your kid, may have noticed something on the packaging saying what the scale was. It's the same principle from a three-dimensional model or a kid's toy to a map of the world. Same principle work. And of course, there are different kinds of maps. You've got the general purpose or reference map. This is different from projection. Projection is shape. Use is a type. Reference map or location map. Display one or more features, either natural or man-made. Water features and shapes of elevation, terrain. Can code cultural features in transportation routes, settlements, and so forth. That's a general purpose map. For example, this here, this is a general purpose map. Now, a political map shows artificial boundaries. That is, the boundaries developed by politicians. This is a political map because you see all the different countries and all the different boundaries here, there, and everywhere. All the maps around the room, those are basically political maps. An interesting thing about maps is they figured this out. You don't need any more than 4 colors to show different areas in different states and provinces and so forth, because they're not going to overlap these colors aren't going to mix and blend together very much. So I need 4 colors, and some have a lot more than that. A topographic map shows just that, topography, shape and features of the terrain. You also have thematic or special purpose maps. Map designed to show just one specific thing, like locations of Walmarts all over the country, all over Arkansas. That's a thematic map. ArcGIS maps are often used for creating a lot of special purpose maps. Now, the principal means of showing elevation topographic maps may be through contour lines. Whereas here on this map, these are represented by color, but they can also be represented by different lines. It's easier with that when you're using maps with a larger scale, looking at a smaller area more specifically. But for large maps like this one, like I say, colors are used more often. And what is the agency that compiles topographic information and mineral resource information in the United States? The United States Geological Survey. They have a website, usgs.gov, really interesting, very useful, very strongly recommended. Some have shaded relief maps. There's a supplemental graphic effect of a topographic map, as if you're looking at it through shadows. You'll see this a lot on maps that try to portray mountain ranges and so forth. They show these kind of jagged, lightly colored lines along a mountain range to represent mountains, as if you're looking through the looking through the shadows and so forth. You see that a lot on this map over here in the side of the room. It looks like the mountains look like they're casting shadows. That effect is called, again, shaded relief. And point symbols. Symbols can represent various points of interest. They can be any shape, any form, but most commonly a dot, particularly with a city. And of course, maps can always be used to show variation and determination of a number, dots, different sizes, circles, and so forth, different shapes. For example, larger cities on maps sometimes portrayed as a larger circle, or sometimes they'll have like a specific shape trying to represent the city boundaries of it. Like say road maps, like this one here of Arkansas. Most of the little towns like Fordyce, Smackover, Sheridan are represented as dots. Now some maps, they bigger the dot, the bigger city, and even large cities like Little Rock might be represented as a dot. But usually, like street maps, they aren't dots, they are shapes, the relative shape of the incorporated area, like with Little Rock, Fort Smith, Memphis, and so forth. Texarkana. And of course, you also have something sometimes called a cartogram. That's especially used to kind of show relationships in numbers between different areas. It's like, you'll see this a lot during the election, showing, let's say, electoral college maps showing the bigger states with bigger electoral votes as bigger states, and the ones with smaller numbers of electoral votes as smaller states. Like, for example, Massachusetts, which is fairly tiny, it'd be very big on a map, on a cartogram of the electoral college, but North and South Dakota, which have very few people living there, it's very small. And choropleth maps are maps used to show the amount of phenomena, which varies from area to area. Of course, maps there are very useful, but again, sometimes they're changed for different reasons. For example, most of the world uses a map with the prime meridian as the center of the Earth to show its relative position in terms of the rest of the world. But different countries use different ways. A lot of maps of the United States showing the world will show the United States, North and South America as the center of it, and the oceans on the side. Russia will basically start with the middle of Russia as the middle of the map, and showing everything else inside of it. Sometimes I've been, like for example here, this one having the prime meridian in the middle of it, a little bit of Russia's cut off here, because it's just such a big country. But a Russian map of the same projection would have Russia in the middle of it and everybody else cut off. And during the Cold War, and especially in totalitarian regimes, maps sometimes will be purposely distorted in order to prevent fears of sabotage or invasion, or just to keep people from escaping. Soviet Union was notorious for this. They routinely distort maps they give out to the people to confuse enemies, saboteurs, and to try to keep people from escaping. Because they couldn't tell exactly where the border was because the landforms are distorted. Or maybe a river on a map that isn't there in real life. Or the border could be represented by a river that isn't on the map. So people don't really know where they are. So those are different map types. Now, what we got to go for now. We'll pick up more on this later. Any questions?